Hello everyone, welcome once again back to the Learning Management System initiative of the Department of Collegiate and Technical Education. So myself, Rekati, a selection grade lecturer of Department of Chemical Engineering (SJP), is here once again to teach you a course on mass transfer to a sixth semester chemical engineering subject under the Diploma in Chemical Engineering program. So today we have to talk about the first unit of the course mass transfer to which is titled as extraction. So today's is the first session of extraction. So before we proceed to the contents of today's class, let me tell you briefly about the objective of this course. It is the objective of teaching this course to the students of diploma in chemical engineering course. So at the end of the course, the student will be able to illustrate the principles and also identify the fields of applications and equipments and solve related problems of the various mass transfer operations and equipments involved. So this is our course objective. And coming to the course outcome of the first unit, that is extraction. So after a student finishes studying the first unit, he or she will be able to explain the principles and identify the various fields of application of liquid extraction and will be able to choose a suitable solvent for the given duty of extraction and also appreciate the use of triangular charts and classify and also illustrate the operation of various extraction equipments. So this is the course outcome that we are looking forward to achieve from each student after having undergone this particular unit. So let me now take you to the list of contents of the present session. So we'll start with the introduction to the unit. Then we are supposed to discuss today about the principles of the extraction operation called generally as liquid to liquid extraction. So we'll also come across the important terminologies that are used in liquid extraction. So here we are also supposed to discuss about the examples of liquid extraction and what is the principle that is involved in the operation to separate the components of the given mixture. Okay, so in the introduction part, we are discussing about two techniques having uh, one big similarity with respect to the principle used. Okay, there is a technique used for removing one component from either a solid or a liquid mixture, and that technique is by using a liquid solvent. Okay, so this technique fall into two categories, and the first category is called the leaching, and it is also called as solid extraction, and the second one is called as liquid extraction. So whenever you're given a mixture and if you're using another liquid solvent to affect the separation of that mixture, then such an operation fall into two categories. One is a solid extraction in which a soluble component from a solid is removed using a liquid solvent. Another one is a liquid extraction in which a liquid component of a liquid solution is removed using another immiscible solvent. So that is what you call as an extraction operation. It can either be a solid extraction or a liquid extraction. Okay. So leaching, which is also called as solid extraction, is that operation used to dissolve a soluble matter from its mixture. Means essentially it's a solid mixture and one of the component will be soluble in a particular solvent. Okay, removal of that soluble matter from its mixture with an insoluble solvent is called leaching or solid extraction, whereas Liquid extraction is that operation used to separate two miscible liquids by the use of a solvent which preferentially dissolves one of them. That means, suppose uh, you have two miscible liquids in a solution, so it's a liquid solution, and if one of the solvent is selected which preferentially dissolve any one of these two liquids, then if that is used to separate two miscible liquids in the given solution, then it is known as liquid extraction. So that is the introduction to a mass transfer operation in which a liquid solvent is used to effect a separate from the given original mixture. Okay. Now let us concentrate on a liquid-liquid extraction, which is also called as liquid extraction in short, or sometimes it is also termed as a solvent extraction. Okay, this is the definition of liquid-liquid extraction. It refers to an operation in which the components of a liquid mixture are separated by contacting it with a suitable insoluble liquid solvent that preferentially dissolves one or more components. That means whenever you are having a task of separating the components of a liquid mixture, then if you go for selecting a suitable insoluble liquid solvent that can dissolve one or more components from this original mixture, then the operation is termed as liquid-liquid extraction. So this is one operation that is preferred whenever a mixture of liquids cannot be that easily separable by distillation. So that means whenever you're given a liquid mixture and you're asked to separate components, so first choice is always a distillation. Okay, because the distillation is one operation which gives you the separation of a liquid mixture in a single processing step to give almost pure components. So that fact makes the distillation the primary choice whenever you're supposed to separate the mixture of liquids. Okay, there are some cases when that separation by distillation is not easy. In other words, whenever the separation by distillation is ineffective or very difficult, then liquid extraction is employed. So, if the separation by distillation is possible, but it is not that effective, means no effective separation is given by distillation, or if the separation by distillation of the given mixture of liquids is very difficult, then you will follow extraction as a choice. So these are some instances where you consider extraction in the place of distillation. So you know what is a close boiling mixture? The liquid mixtures having um, a very close boiling points. Means the relative volatility of such mixtures is not that great. So you know that relative volatility is very important. So if it is very less, then separation by distillation is not that easy. So for such mixtures, and also for the mixtures containing substances which cannot withstand very high temperature that is involved in distillation, even under vacuum. So whenever heat sensitive materials are to be separated using distillation, then vacuum distillation is carried out. You know this fact. Even in that condition, if the substances are so sensitive that they cannot withstand the temperature, then the only alternative is liquid extraction. ಸೊ ಈ ಥರ ಕೇಸ್ಗಳು ಇದ್ದಾಗ ಕ್ಲೋಸ್ ಬಾಯ್ಲಿಂಗ್ ಮಿಕ್ಸ್ಚರ್ಸ್ನ ಸಪರೇಟ್ ಮಾಡಬೇಕಾದಾಗ ಅಥವಾ ಹೀಟ್ ಸೆನ್ಸಿಟಿವ್ ತುಂಬ ಹೀಟ್ ಹೈ ಟೆಂಪರೇಚರ್ನ ವಿತ್ಸ್ಟ್ಯಾಂಡ್ ಮಾಡೋಕ್ಕಾಗದೇ ಇರೋವಂಥ ಸಂದರ್ಭದಲ್ಲಿ ನಾವು ಎಕ್ಸ್ಟ್ರಾಕ್ಷನ್ನ ಸೆಲೆಕ್ಟ್ ಮಾಡಬೇಕು, ನಾಟ್ ದ ಡಿಸ್ಟಿಲೇಷನ್, ಟು ಸೆಪರೇಟ್ ದ ಮಿಕ್ಸ್ಚರ್ ಆಫ್ liquids. So that is the choice of operation to separate a liquid mixture. Okay, So let us now briefly understand how a separation can be achieved in liquid extraction. So in this operation means in liquid extraction, solvent is added to the original liquid mixture. So just like all other mass transfer operations, here also you should have two phases. So one is the liquid mixture from which you need to separate the component. So it is called as original liquid mixture or feed liquid. So to this mixture, you will be adding a solvent, so which is another liquid phase. So as a result, two immiscible layers are formed, both containing varying amounts of different components. See, the solvent that you are adding to original liquid mixture is insoluble in the mixture. Okay, however, it can dissolve some of the components from the original liquid mixture. So when such a solvent is added to the liquid mixture, two immiscible layers will be formed. So two liquid layers that are not miscible in each other will be formed, and both will contain all the components but in a very different amounts. Okay, uh, the concentration of the three components, one is a solvent, one is a component that is being removed in the given mixture, and the components that is not soluble in the solvent. So all these three components will get distributed between the solvent phase and the another liquid phase from which you are separating the components, but in very different amounts. So both the liquid phases that are resulting will contain varying amounts of different components. So after you add the solvent and allow the components to get distributed between the two layers, the layers will be separated. Okay, so these isolated or separated layers, these two layers will be separated using density difference. As the two layers are immiscible, we can easily separate them from one another. That is the second step. And after separating, you can take out the solvent used, or you can recover the solvent used from each of these phases. So that is the end of the operation. Okay. So in this operation, the separation of the components of the solution depends upon the unequal distribution of the components between the two immiscible liquids phases. That means, as I told you already, so as some of the components of the original mixture is highly soluble in the solvent and some other very less soluble. So due to this fact, the components present in the system gets distributed unequally between the two phases. So that is, the separation of the components of the given liquid solution depends upon the difference in solubilities of the components in a suitable solvent. So that unequal distribution of the components is due to the difference in the solubilities of the components in the given solvent. So whichever suitable solvent that you're selecting for the operation. So in this, as I said already, the various components are soluble to different extents, quite different extents. So that is called as difference in solubilities of the components in the given solvent. So extraction utilizes the difference in solubilities of the components or constituents in a given solvent to effect a separation. So it is the difference in solubilities of the components that is responsible for separation from the original liquid mixture. So that is how we can achieve a separation in liquid extraction operation. So at the end of the operation, as I said, you have to recover the solvent from the two layers and reuse the solvent, and for that recovery again you have to go for a distillation method only. Okay, so here the distillation will not be very difficult because um, the relative volatility of the components in the given mixture will be very high. So as a result of that, we can easily recover the solvent from the resulting layers in the operation using again a distillation. That means the extraction operation is a not a single step operation, it involves many steps, and the final step is recovery of the solvent, which is again done by using distillation. Okay. So in the operation, whichever feed solution or the original solution that you consider, from which you need to make a separation of the constituents, represents one of the phases. So as I said initially, there are two phases in the operation. One phase is the feed solution. The other phase, the second phase, is the solvent phase. So whatever solvent that you're adding to feed solution to dissolve some of the components or one of the component, that represents the second phase. So the two are immiscible in each other, as I said already. So the two immiscible phases in contact are both liquids. So is a liquid-liquid operation involving transfer of a soluble component of the liquid mixture into another solvent. So feed solution is a liquid mixture. There is a transfer of a component from feed solution to another phase, that is solvent phase. So here there is a mass transfer from one liquid solution to another liquid solution. So the operation is liquid-liquid operation. So it is a liquid to liquid mass transfer operation that involves the transfer of a soluble component of a liquid mixture into another liquid solvent. So sometimes we also call liquid extraction a solvent extraction. So because the solvent that is used in the operation will have a close affinity to one or a group of the components from the original solution. Okay. So it is termed as solvent extraction as two or more liquids forming a homogeneous mixture are separated by contacting with another liquid solvent into which one or a group of the components dissolve or separate out easily, that is preferentially. So it is a solvent ability to dissolve some of the components from the feed solution is responsible for separation in the operation. So it is sometimes also termed as solvent extraction. So distillation and extraction are both used for separation of the components of liquid mixture based on the relative merits and demerits of the individual methods. So whenever you are given a liquid mixture to separate into components, there are two options for you. One is distillation, other one is extraction. So as I already told you in the previous slide, distillation is always the primary choice and extraction is always a secondary choice. So that is because distillation is a single step operation. So it is comparatively or relatively easier when it is compared to extraction, which is a multiple step operation. So the combined step operation extraction is quite complicated in comparison to distillation. So whenever you have a mixture that is easily separable by both distillation and extraction, so the choice will always be distillation. So only when distillation is very difficult, very ineffective, and in some unusual situations only, you can go for extraction, not the distillation. So like this, the relative merits and demerits of both these operation will have to be considered to decide whether distillation is followed or extraction is used. ಸೊ ಯಾವಾಗ ನೀವು ಲಿಕ್ವಿಡ್ ಮಿಕ್ಸ್ಚರ್ನ ಸಪರೇಟ್ ಮಾಡಬೇಕಾಗುತ್ತೋ ಆವಾಗ ಡಿಸ್ಲೇಷನ್ ಆದರೂ ಯೂಸ್ ಮಾಡ್ಬೋದು, ಎಕ್ಸ್ಟ್ರಾಕ್ಷನ್ ಆದರೂ ಯೂಸ್ ಮಾಡ್ಬೋದು. ಸೊ ಬಟ್ ಡಿಸ್ಲೇಷನ್ ಯಾವಾಗಲೂ ಮೊದಲನೇ ಚಾಯ್ಸ್ ಆಗಿರುತ್ತೆ. ಯಾಕೆ ಅಂದರೆ ಡಿಸ್ಲೇಷನ್ ಒಂದೇ ಸ್ಟೆಪ್ಪಲ್ಲಿ ನಿಮಗೆ ಸಪರೇಷನ್ನ ಕೊಡುತ್ತೆ. ಸೊ ಅಂದ್ ಕಾಂಪೊನೆಂಟ್ಸ್ ಯಾವುದು ಸಪರೇಟ್ ಆಗುತ್ತೋ ಅದು ಕೂಡ ಪ್ಯೂರ್ ಕಾಂಪೊನೆಂಟ್ಸ್ ಸಿಗುತ್ತೆ ನಿಮಗೆ. ಸೊ ಆ ರೀಸನ್ಗೆ ಡಿಸ್ಲೇಷನ್ನ ಯಾವಾಗಲೂ ಫಸ್ಟ್ ಚಾಯ್ಸ್ ಆಗಿ ಯೂಸ್ ಮಾಡ್ತೀವಿ. ಯಾವಾಗ ಡಿಸ್ಟಿಲೇಷನ್ ನಮಗೆ ರಿಕ್ವೈರ್ಡ್ ಸಪ್ರೇಷನ್ ಕೊಡೋದಿಲ್ವೋ ಆಗ ನಾವು ಎಕ್ಸ್ಟ್ರಾಕ್ಷನ್ನ ಚಾಯ್ಸ್ ಆಗಿ ತಗೊಳ್ತೀವಿ. ಸೊ ಡಿಸ್ಟಿಲೇಷನ್ನ ಯಾವಾಗಲೂ ಪ್ರೈಮರಿ ಚಾಯ್ಸ್ ಅಂತ ಕನ್ಸಿಡರ್ ಮಾಡಬೇಕು, ಎಕ್ಸ್ಟ್ರಾಕ್ಷನ್ನ ಸೆಕೆಂಡರಿ ಚಾಯ್ಸ್ ಅಂತ ಕನ್ಸಿಡರ್ ಮಾಡಬೇಕು. A typical liquid-liquid extraction utilizing the difference in solubilities of the components of liquid mixture may be described as consisting of the following steps. So now let us see what are the different steps involved in the extraction operation. The first step is contacting the feed with the solvent. The second step, separation of the resulting phases. The third step and the final step is removal or recovery of solvent from each resulting phases. So the first and the very important step is contacting the feed solution with the solvent phase. So the two liquid phases are thoroughly contacted here because that contact only help in separating out the components by causing the redistribution of the components of the feed between the two phases. Okay, so after that contacting is over, you need to separate the two resulting immiscible phases. And after separating out the phases, whatever that is left is a recovery of the solvent. Whatever solvent is present now at the end of the operation, usually in the form of a solution. So the solvent coming out will be a solution with a dissolved component from the feed. So from that you have to separate out the pure solvent so that you can reuse that solvent in the operation. So that is your final step, and as I already mentioned, it is always done, or most of the case it is done using distillation. So the third step usually will be the distillation for the liquid-liquid extraction operation. So this is the reason why liquid extraction is the secondary choice. So liquid extraction is three-step operation. So it is a bit complicated compared to the single step operation of distillation. So with that reason, we usually consider extraction as the secondary choice and distillation as the primary choice. Okay, so this is a simple flow diagram to explain how extraction is conducted. Okay, so this block, let us assume, represent a equipment in which liquid extraction is carried out. So as understood, there are two phases that should enter the equipment, and the two phases after getting contacted inside will go out of the equipment. So one of the phase that is entering is the feed solution. So feed solution means it's the original solution from which you need to make the separation of components. Another phase that is entering the operation is solvent, which is also called as extractant. So and both these two phases entering are liquids essentially. Okay, so let us now see what a feed solution contains. So feed solution uh, is a group of constituents. Okay, uh, one constituent or a group of constituent that is not soluble in the selected solvent constitutes the feed solvent, and the another component or a group of components which is soluble or which is getting removed in the operation, soluble in the solvent that is selected, represents the solute liquid component. So this is how we can classify the components of a feed solution. So ಯಾವ ಕಾಂಪೊನೆಂಟ್ ಸಾಲ್ವೆಂಟ್ ಅಲ್ಲಿ ಡಿಸಾಲ್ವ್ ಆಗೋದಿಲ್ವೋ ಅದನ್ನ ಫೀಡ್ ಸಾಲ್ವೆಂಟ್ ಅಂತ ಕರಿತೀವಿ. ಅಂಡ್ ಯಾವ ಕಾಂಪೊನೆಂಟ್ ಅಥವಾ ಗ್ರೂಪ್ ಆಫ್ ಕಾಂಪೊನೆಂಟ್ಸ್ ಸಾಲ್ವೆಂಟ್ ಅಲ್ಲಿ ಸಾಲ್ಯುಬಲ್ ಇದೆ, ಸಾಲ್ಯುಬಲ್ ಆಗಿ ಅದು ರಿಮೂವ್ ಆಗುತ್ತೆ ಆಪರೇಷನ್ ಅಲ್ಲಿ, ಸೊ ದಟ್ ಈಸ್ ಕಾಲ್ಡ್ ಆಸ್ ಸೊಲ್ಯೂಟ್ ಲಿಕ್ವಿಡ್. So we are using that liquid term here because whichever component that is undergoing mass transfer operation is also a liquid component. Okay, so these two phases enter the operation, and inside the equipment they are thoroughly contacted so that the components gets distributed between the phases, and after the contacting is over, we are allowing the phases to separate due to density difference, and after that the two phases are separately taken out of the equipment. So one of the phase that is coming out is a solvent rich phase, means whatever solvent is entering here, so that will dissolve the solute liquid from the feed solution and go out as a phase. So that liquid phase in which solvent is rich, which contains almost all the solvent that is entering the operation, is called extract phase. The another phase, that is a feed solution from which the solute liquid has been removed, means, so this is one phase which is lean in the extraction solvent. So that phase coming out is called raffinate phase. So, and it is solvent clean phase, which is mostly containing the feed solvent or the original solvent. So this is how the extraction operation is usually carried out. The solution which is to be extracted is called the feed, and the liquid with which the feed is contacted for the extraction purpose is called the solvent. Okay, so this is the feed, this is the solvent. These are two phases, liquid phases that are involved in the operation. The liquid component which is to be removed from feed is called the solute liquid. ಸೊ ಯಾವ ಕಾಂಪೊನೆಂಟ್ನ ನಾವು ಸಪರೇಟ್ ಮಾಡ್ತಾ ಇದ್ದೀವಿ ಆಪರೇಷನಲ್ಲಿ ಅದನ್ನ ಸೊಲ್ಯೂಟ್ ಲಿಕ್ವಿಡ್ ಅಂತ ಕರಿತೀವಿ. ಇನಿಷಿಯಲಿ ಇಟ್ ಇಸ್ ಪ್ರೆಸೆಂಟ್ ಇನ್ ಫೀಡ್ ಸೊಲ್ಯೂಷನ್. At the end of the operation, it will be present as a solution in the solvent. The other component or a group of components is called original solvent or feed solvent. So, E component. So, E component remove ಆಗ್ತಾ ಇಲ್ಲ operation ಅಲ್ಲಿ because this component is not soluble in the solvent. Okay, ಇದು single component ಆಗಬೇಕಂತಿಲ್ಲ. It is a group of all other components in the given feed solution that is not soluble in the extraction solvent. So that part of the feed solution is called original solvent or feed solvent. It's also sometimes called as diluent. Okay, so those are the terminologies that are used in liquid extraction. You need to remember them. Okay, so that is the original solvent or feed solvent or diluent. The mass transfer of solute liquid takes place from feed solution to solvent phase. Okay, so inside the equipment, it is a solute liquid that is getting transferred into the solvent phase. So this is the direction of mass transfer from feed solution to solvent phase. The solute liquid gets transferred. It is a unidirectional mass transfer operation. The residual liquid solution, which is solvent lean phase, from which the solute is removed, is called the raffinate phase or raffinate layer or simply raffinate. Okay, so the residual, whatever that thing that is left in the feed solution at the end of the operation from which the solute has been removed is called the raffinate phase or raffinate layer. And the solvent rich product means the another phase which is rich in solvent and the solute liquid is called as the extract phase or extract layer. So these two are the products of the operation. One is extract phase, it's a solvent rich phase which contains most of the solute liquid. And the another phase is called the raffinate phase, which is a residue of the operation, means from which the solute liquid has been removed. So it is called solvent lean phase because it might contain a small amount of the solvent that is used in the operation. Okay, so let us understand extraction operation with this example. Consider a solution of acetic acid and water. So you have a binary solution of two components, one is acetic acid, one is water, and contact this solution with the solvent like ethyl acetate. So ethyl acetate is the liquid that is selected in the operation to act as a solvent or extractant. So when you add to this original mixture the solvent ethyl acetate, then two phases or layers will result because this phase is insoluble in this original solution. So the two immiscible phases or layers that will result contain in fact all the three components. There is acetic acid, there is water as well as ethyl acetate in both extract and raffinate phase, but in a very different composition. So the extract phase or layer, in this particular instance, we can call that as a ester layer also or as organic layer. So because it contains the ester ethyl acetate. Okay, so in this layer means the extract layer, um, whatever that is present is most of the acetic acid and ethyl acetate. So ethyl acetate is rich in this phase. Also, the acetic acid, which is a solute liquid here. Okay, so this acetic acid and ethyl acetate will form the extract phase in this particular example, and the raffinate phase, which can be called here as a aqueous layer, because whatever that is present in the residual liquid after the contact is containing water. So the raffinate phase is the aqueous layer in the operation, which contain weaker acetic acid solution. Means a small amount of acetic acid might have been left over in the phase, along with a very small amount of ethyl acetate also. So this is the composition of the raffinate phase in this particular example of extraction. So it contains mostly water, so it is called aqueous layer, and a small amount of acetic acid and ethyl acetate may be present. So that is how we can achieve a separation using liquid extraction operation. The amount of water in extract and ethyl acetate in the raffinate, the amount of water in extract and that of ethyl acetate in the raffinate depends upon the solubilities of one into the another. So, in this particular example, acetic acid is very soluble in ethyl acetate, but water is very slightly soluble in ethyl acetate. So that means the solubility of water and ethyl acetate is very, very less. So, however, depending upon that solubility, some amount of water may get added to ethyl acetate. At the same time, a small amount of ethyl acetate may also get dissolved in water. So the amount of this in the extract phase, amount of ethyl acetate in the raffinate phase depends upon the solubility of one into the other. So in this particular example, water is the feed solvent, which is also called as diluent, as I mentioned in previous instance, and acetic acid is the solute liquid. Okay, this is the one which is getting transferred in the operation. Then ethyl acetate is the extraction solvent. So it is called as a solvent or extractant. So extraction operationally ಎರಡು liquid phase ನ ಕಾಂಟ್ಯಾಕ್ಟ್ ಮಾಡ್ತೀವಿ. ಒನ್ ಈಸ್ ದ ಫೀಡ್ ಸೊಲ್ಯೂಷನ್, another one is solvent phase. ಸೊ ಎರಡನ್ನು ಕಾಂಟ್ಯಾಕ್ಟ್ ಮಾಡಿದಾಗ ಏನಾಗುತ್ತೆ, ಈ ಥರ ಎಕ್ವಿಪ್ಮೆಂಟಲ್ಲಿ ಸೊಲ್ಯೂಟ್ ಲಿಕ್ವಿಡ್ ಅಂತ ಏನಿರುತ್ತೆ, ಈ ಕಾಂಪೊನೆಂಟು ಫೀಡ್ ಸೊಲ್ಯೂಷನಿಂದ ಸಾಲ್ವೆಂಟ್ ಫೇಸಿಗೆ ಟ್ರಾನ್ಸ್ಫರ್ ಆಗುತ್ತೆ. ಸೊ ದಟ್ ಈಸ್ ಅ ಮಾಸ್ ಟ್ರಾನ್ಸ್ಫರ್ ಅಕರಿಂಗ್ ಇನ್ ದ ಆಪರೇಷನ್. ಆ ಟ್ರಾನ್ಸ್ಫರ್ ಆದಮೇಲೆ ಎರಡು ಫೇಸಸ್ನ ಸಪ್ರೇಟ್ ಮಾಡಿದಾಗ ಒಂದನ್ನ ಎಕ್ಸ್ಟ್ರಾಕ್ಟ್ ಫೇಸ್ ಅಂತ ಕರಿತೀವಿ. ಸೊ ಅದರಲ್ಲಿ ಸಾಲ್ವೆಂಟ್ ಮತ್ತು ಸೊಲ್ಯೂಟ್ ಲಿಕ್ವಿಡ್ ಜಾಸ್ತಿ ಕ್ವಾಂಟಿಟಿಲಿ ಇರುತ್ತೆ, ಬಟ್ ಫೀಡ್ ಸಾಲ್ವೆಂಟ್ ಸ್ವಲ್ಪ ಕ್ವಾಂಟಿಟಿಲಿ ಮಾತ್ರ ಇರುತ್ತೆ. ಸೊ ವೆರಸ್ ಅನದರ್ ಫೇಸ್ ಕಮಿಂಗ್ ಔಟ್ ಮೀನ್ಸ್ ದ ಇನ್ನೊಂದು ಫೇಸ್ ಬರ್ತಾ ಇದೆಯಲ್ಲ ಆಪರೇಷನಿಂದ, ಸೊ ದಟ್ ಈಸ್ ಕಾಲ್ಡ್ ರಾಫಿನೇಟ್ ಫೇಸ್. ಆ ರಾಫಿನೇಟ್ ಫೇಸಲ್ಲಿ ದ ಫೀಡ್ ಸಾಲ್ವೆಂಟ್ ಜಾಸ್ತಿ ಕ್ವಾಂಟಿಟಿಯಲ್ಲಿ ಇರುತ್ತೆ. ಸೊ ಎಲ್ಲ ಫೀಡ್ ಸಾಲ್ವೆಂಟ್ ಆಲ್ಮೋಸ್ಟ್ is coming out in the raffinate phase along with a small amount of the solvent and a small amount of the solute liquid. So that phase is called raffinate phase. Okay. So now we have understood the principles of liquid-liquid extraction. So this is one pictorial representation to show you how a liquid extraction gives a separation of the components from a original mixture. So ಈ beaker observe ಮಾಡಿ, you have two phases, right? Two immiscible phases. Okay, one phase solvent represent ಮಾಡಿದ್ರೆ, this phase is representing a liquid solution. So this is your original liquid solution from which you want to separate the component that is dissolved in the solution. Okay, ಇಲ್ಲಿ you can see the two components. So symbolically ಎರಡು ಕಾಂಪೊನೆಂಟ್ ಇದೆ ಈ ಮಿಕ್ಸ್ಚರ್ ಅಲ್ಲಿ, ಒಂದು ಗ್ರೀನ್ ಕಲರ್ ಅಲ್ಲಿ, ಇನ್ನೊಂದು ರೆಡ್ ಡಾಟ್ ಫಾರ್ಮ್ ಅಲ್ಲಿ. ಸೊ ಇನ್ ದಿಸ್ picture, so this layer represents the feed solution and this yellow layer represents the solvent phase. The feed solution contains two components, one in green color, one in red color in the form of dots. So ಇದನ್ನೇ ಏನು indicate ಮಾಡ್ತಿದೆ ಅಂದರೆ one component is in the dissolved state in the given mixture. When you add the two in a single vessel, ಏನಾಗುತ್ತೆ ಎರಡೂ ಕೂಡ immiscible ಆಗಿರೋದ್ರಿಂದ they'll not dissolve in each other. Okay, so they'll stand as a separate layers. ಎರಡು separate layer ಹಾಗೆ ನಿಂತ್ಕೊಳ್ಳುತ್ತೆ. So here to establish a contact between the two properly, you need to agitate the entire mass. So that is very important since the two faces are immiscible in each other. The proper contact between the two faces can be achieved only by mixing the whole mass. So when you mix the liquid mass in the beaker, what is happening? So one of the liquid phase is getting dispersed in the another liquid phase in the form of droplets. So the yellow color solvent phase illi small droplets ತರ convert ಆಗಿದೆ because of mixing. So now what you have in the second diagram is the emulsion. So when two immiscible liquids are agitated thoroughly mixed, what you get is emulsion, not the solution. Okay, so now there is a large area of contact between the two phases. When this condition is achieved, one of the component is getting transferred into the another phase from the original solution. So the green part represents the original solution. From here the red dots are getting added to the yellow dots, indicating that there is a transfer occurring from the feed solution into the solvent phase. So after you stop mixing, again the two liquid phases will separate out as one top layer, one bottom layer. So top layer is a lighter one, the bottom layer is the heavier one. So now you can make out the difference here. Originally the solvent phase was a pure solvent. Now it is having another component in dissolved state. That means it has dissolved one of the component from the original solution into the solvent phase. Okay, so mass transfer from this phase to this phase has taken place now. So after this, by applying settling, you can separate out the two phases, and since they are immiscible, you can easily decant out the two liquids separately into two separate beakers, and one beaker contains the yellow color liquid along with the red dots that was initially present in the original mixture, and that mixture is called extract phase. And the other layer taken out in the second beaker is the raffinate phase, because this is the one phase from which the solute has been removed, that is dissolved out into the given solvent. So this is the extract phase or extract layer, and this is the raffinate phase or raffinate layer. Another picture explaining you how separation occurs in extraction. So you have a vessel here where there are two immiscible liquid phases. One liquid you can see it's one which is indicated with the purple color. So this part represents the solvent liquid phase. Okay, so this is the solvent, and the one at the bottom is the feed solution. Okay, so this is a heavier phase and this is a lighter phase. So the feed solution, as you can see, is not a single component solution. It has three components. One is a orange color component, one is a red color component, one is a green color component. That means there are three components in the given liquid solution. Okay, so when you add the two liquid phases and mix them thoroughly, so this is what is resulting. Okay, so here what you have is emulsion. That means the solvent phase, that is the light phase, has been dispersed in the form of droplets throughout the original solution phase. Now we are now presenting a large surface area of the solvent to contact the original liquid phase, and due to this kind of contact, one of the component which is having high solubility in the solvent phase is getting dissolved in the solvent. You can see the red dots representing one of the component is getting transferred from the original liquid solution to the solvent phase. Okay. So this is the transfer of mass occurring. So in the emulsion, the continuous phase is the feed solution in this example, and the dispersed phase, the purple dots, so what you can see, that represents the dispersed phase. So once the transfer is complete, you can apply separation. That is, you can allow the liquids to settle out. So during that, again, two liquid phases get separated, and now the solvent is now having another component, that is a solute liquid component dissolved. So one of the component from this phase has been transferred to the solvent phase. Okay. Now this is the end of the operation. You have two liquid phases again. One is the extract phase, solvent rich phase. Other one is the raffinate phase. That is the solvent lean phase. Okay. So this is how we can represent a liquid extraction in the laboratory. So all of you know what is this? This is a separatory funnel, and into this separatory funnel, you can take one solution, that is an organic compound dissolved in water. So that aqueous solution is taken, and after that, one solvent layer, so a suitable solvent which can dissolve the organic compound, is taken into the same separatory funnel. So when the solvent is added, you can see that two liquid phases will stand separately. So one at the top, one at the bottom, because they are immiscible. Okay. So now to establish a contact, proper contact between the two, a thorough contact, you need to shake the separatory funnel. So when the funnel is shaken, the two liquid phases will get thoroughly mixed in each other, and in that condition, the organic compound that was initially in the aqueous phase will get added or dissolved in the solvent phase. So due to that dissolution or the transfer of component from this phase to this phase, so at the end, if you allow the liquids to again separate out into two phases, the top layer is a mixture now. It is not a pure solvent. The solvent along with the organic compound that has been transferred from here to here. The bottom phase is the aqueous layer, means containing almost only water, because all the organic compound that was initially here has been now dissolved in the solvent phase. So this is the extract phase and this is the raffinate phase. So this is a picture before extraction, and this is what you can see after extraction. Okay. So that completes the understanding of principles involved in liquid-liquid extraction operation. So let me just take you through a few definitions that are used in liquid extraction. So the important terminologies, and after that we will end the first section. So one important definition is distribution coefficient represented by K. So in a dilute solution at equilibrium, the ratio of concentration of solute in two phases is called as distribution coefficient or distribution constant at K. So when the two liquid phases are contacted in operation, at the end means, and when equilibrium has reached between the phases, so what is the concentration of solute in the two phases? That is measured, and the ratio of these concentration in the two phases at equilibrium is known as distribution coefficient, which is also called as distribution constant, represented by capital K. So in the form of equation, we can write the distribution coefficient as K equals CE by CR, where CA represents the concentration of solute in the extract phase, and CR represents concentration of the solute in the raffinate phase at equilibrium. Okay, so this ratio is distribution coefficient. So distribution coefficient can be expressed in any concentration terms. So if it is represented using the concentration term, this will be the equation. On the other hand, if you represent the concentration of the component in the form of or in terms of weight fraction, then you can write down the equation like this. So K dash is equal to Xe by Xr. So where Xe represents the mole or the weight fraction of the solute in extract phase. So E stands for extract, R for raffinate. So in the same way, XR represent the weight fraction of solute in the raffinate phase. The ratio of these two quantities is known as distribution coefficient. So distribution coefficient is one of the factor that helps in selecting the solvent in the given operation. So for a given solvent, we expect that the distribution coefficient is very high. So whenever you have a number of solvents, by measuring the distribution coefficient, you can select the best out of the available choices. So that is the significance of distribution coefficient. Another important terminology that is used in extraction is selectivity, which is denoted by beta. So it is also one of the important factor that is considered to select a suitable solvent for the given duty of extraction. So this is the definition of selectivity or beta. It is the ratio of concentration ratio of solute to feed solvent in extract phase to the same ratio in raffinate phase at equilibrium. Okay. So Xc andre ಇಲ್ಲಿ concentration of the solute. That means C represents solute. Xa is the concentration of feed solvent. Okay, so that means A represents feed solvent. So this ratio in extract phase, okay, the same ratio in the raffinate phase at equilibrium is what is known as selectivity. Okay, so if you are considering a feed that contains A as a feed solvent, C as a solute liquid, while if you represent the solvent as component B, then Xc and Xa are the weight fractions, or can also represent them in terms of mole fractions of solute to feed solvent in extract phase, and the same ratio in the raffinate phase at both at equilibrium. Okay, the significance of selectivity is it is the one which indicates the measure of separation by extraction. That means how much separation is possible from the extraction operation using a given solvent. So that is indicated by the factor selectivity. That is the value of selectivity gives you this quantity. It has the same significance in extraction as relative volatility has in distillation. Okay, you know what is relative volatility in distillation? It is the measure of separability by distillation. Separation factor ಅಂತ ಕೂಡ ಹೇಳ್ತೀವಿ. The same kind of separation factor is there in extraction, and that is selectivity. That means selectivity is analogous to volatility or relative volatility in distillation. So what is relative volatility in distillation is same as what is selectivity in extraction. So just like how relative volatility, when it becomes 1, tells you that the distillation cannot give you separation, the selectivity also indicates that the separation by extraction is not possible whenever its value is equal to 1. So you always expect that beta value should be greater than 1 if you want the separation to be possible by extraction. So for all practical operations, selectivity should be greater than 1. So this is a condition. So if selectivity is equal to 1, then extraction is not possible. And if it is greater than 1, then the solvent is suitable to carry out the extraction. Okay, so that is all about the introduction to extraction operation. Okay, hope you have understood the concepts. Okay, let me take you through a set of multiple choice questions to help you conduct a self-assessment test so that you will come to know how far you have understood the concepts. Okay, so this is your first question. Dash is used to separate two miscible liquids by the use of a solvent which preferentially dissolves one of them. The options given for this question is leaching, liquid extraction, distillation, none of this. Okay, so leaching cannot be the right choice because leaching is that operation in which a component from a solid mixture, not the liquid mixture, that is separated out. So A is not the right option. C is also not the right option because distillation does not use the solvent to effect a separation. Okay, so whatever that is left out is liquid extraction. So liquid extraction is the right choice for this question as an answer. Okay, so when a mixture of liquids is not easily separable by dash, that is when separation by dash is ineffective or very difficult, then liquid extraction is employed. Options: absorption, distillation, leaching, none of this. So, which among these four options is the right answer? So, think among yourself before I give you the right answer. Okay, I hope all of you guessed the right answers. It is this distillation. So, whenever a liquid mixture is there for separation, so first choice is always distillation. And if distillation is ineffective or very difficult, then extraction is used. So answer is B. So extraction is usually followed by dash for the recovery of the solvent. For the recovery of solvent, which operation is usually used? Is it distillation? Is it evaporation? Is it absorption? Is it none of this? Okay. See, among these options, it is either the distillation or evaporation. In fact, recovery of solvent in extraction operation at the end of the operation is usually done by distillation, but in some cases it is also done using evaporation. But in most of the cases it is distillation. So, because of that fact, our right answer for this question is distillation. Separation of acetic acid from water using ethyl acetate is an example for leaching, liquid extraction, distillation, absorption. Okay, acetic acid in water is a liquid solution. Ethyl acetate is also a liquid. So liquid to liquid operation is always a liquid extraction. It is not leaching, which is a solid liquid transfer. It's not the distillation, which is a liquid to vapor transfer. It is not the absorption, which is a gas to liquid transfer. So it is liquid extraction, the right answer for this question. In the separation of acetic acid from water using ethyl acetate by extraction, water is called as, okay, options: extract, solute liquid, extractant, feed solvent. So what is water called in this particular instance of liquid extraction? Okay, so hope all of you got the right option. Water is the feed solvent because this is one component that is not getting dissolved in the ethyl acetate So water is the feed solvent. It is also called as original solvent or diluent. Okay. So option D is the right answer. In extraction, the solvent-rich product is called as extract, raffinate, solute liquid, none of the above. Okay, so think properly and come out with the right option. So it is the extract. Okay, solvent-rich product in the operation is always called as extract or extract layer or extract phase. Option A is the answer. In extraction, the solvent lean phase is called as extract, raffinate, solute liquid, none of this. So same options as the previous case. So solvent rich product is extract. So solvent lean product of the operation is of course the raffinate. Option B is the right answer. Liquid extraction sometimes is also called as or termed as solid extraction, leaching, solvent extraction, none of these options. So which among these four is the right answer? What is the another name used for liquid extraction? Okay, so hope all of you guessed the right answer. So it is the solvent extraction because here both are liquids. So solid extraction is not the right term. Leaching is also not the right answer because leaching is another name of solid extraction. It is the solvent extraction which is the right answer for this question. Solid extraction is another term used for solvent extraction, leaching, adsorption, drying. Okay, so solid extraction. I hope we have discussed this in the beginning of the class. So, what is another name of solid extraction? Okay, let me give you the answer. It is leaching. So, leaching is that operation in which a solid component from a solid mixture is removed using a liquid solvent that dissolves that component. It is also termed as solid extraction. Option B is the correct answer. Solid extraction is another term used for. Very sorry, this question has been repeated. Extraction utilizes the difference in dash to effect a separation. Solubilities of the constituents in a given solvent, volatilities of the components, densities of the constituents, none of these. Okay, so which physicochemical property that is being used in the operation to effect a separation, or is it the volatility or is it the physical property like a density, or is it the solubility of the components in a solvent? Okay. So as per our basic definition of extraction, extraction is that operation which uses the difference in solubilities of the components in a suitable immiscible solvent. So option A is the right answer for this question. Extraction, oh God, it's getting repeated, sorry. So This is your last question coming up. In liquid extraction, the mass transfer of the dash takes place from feed solution to solvent phase. So, which component is getting transferred in liquid extraction and what it is called? Is it called as a diluent? Is it called as a original solvent? Is it called as feed solvent or is it called as solute liquid? So, which is the component that is undergoing mass transfer in the operation? Okay, hope all of you got the right answer. It is the solute liquid. The solute liquid, the part of the feed solution which is undergoing mass transfer from the feed to the solvent, is the one that is undergoing mass transfer in the operation. It is not the diluent, original solvent, or feed solvent. So these three terms represent the same component of the solution. So whichever component that is not undergoing mass transfer is called as diluent or original solvent or feed solvent. So the right answer here is solute liquid. Okay, students, that's all for today. So these are a set of YouTube links. Watching these videos, you can understand the concepts of principles of extraction and examples in a visual manner. Please do watch them. So this is a quick recap of what we studied in today's class. So we understood the introduction part where we came across the difference between leaching and liquid extraction and what is the similarity between the two operations. That part also helped you to understand what is liquid extraction is all about. And later on, under the topic principles of liquid extraction, you studied what is liquid extraction, how the operation is carried out, and how we can achieve the separation from the operation. All this we discussed along with few examples. And then under the third part, that is terminologies used in extraction, we understood two important definitions. One is distribution coefficient, other one is selectivity. Also, we came to know the significance of these terms in extraction operation. So with that, let me take leave. I hope you followed the concepts. So see you again in the next session with more discussions on liquid extraction. Thank you for joining me. See you.